Today we're excited to have Professor Marzouk from MIT. We know each other since the day he was, I was younger.
So was I.
You were a baby at the time, okay? All right? So Youssef is one of the most recognized people on uncertainty quantification in all aspects of the topic, with interested application-wise in many domains, from combustion to materials, I noticed, to practically sort of every relevant area. He's a professor at the Department of Aeronautics and Astronautics at MIT. He's going to be talking today on sequential inference via low-dimensional couplings.
Okay, well, thank you, Nicholas, for the introduction and for the invitation. It's been very nice to be here all day with many, many interesting discussions, and good to see what's going on in the center. So today I want to talk about joint work with my, recently graduated PhD student, Alessio Spantini, postdoc Daniele Bigoni in my group, about computational methods for Bayesian inference. And the Bayesian inference methods that we propose are going to involve kind of a combination of ideas from transportation, which I'll define as we go along, and graphical models, and be applied in sort of a range of systems where often the data are arriving sequentially and you need to make inference in an online fashion on the fly. So just to kind of set the stage, I assume most of you worked on Bayesian inference in some way, but to kind of give an example problem, this is actually a picture of geothermal reservoir in New Zealand, where this is kind of a prototypical and challenging Bayesian inference problem that one often wishes to solve from measurements that are sort of indirect, for instance, temperature and pressure in boreholes that are drilled into the surface. One wants to infer things like the permeability field in the subsurface, or maybe the porosity, or maybe the saturation state of the reservoir, or the temperature, spatially distributed. And from the Bayesian perspective, what we can do is write down this inference problem, formalize it using Bayes' rule, where if I let x denote the parameters, so that some discretization of this permeability field, if you will, y denote the data, then what I want to do is explore this conditional distribution of x conditioned on y. Okay? Y are my observations. Here I have a likelihood on the right-hand side, so the probability density of y given the parameters. This might encode a complicated forward model, maybe a PDE model that relates the parameters to the observations, along with some noise, along with some statistical error model, maybe a more sophisticated model of model discrepancy, model misspecification. All these ingredients can go inside the likelihood. Many other ingredients can go inside the prior. I won't really discuss those ingredients. I'm going to focus on the computational task, but I will mention them just so you realize that they're important and non-trivial. But from the computational perspective, if you say, okay, I can write down this posterior density up to a normalizing constant, I want to characterize it in some way. Now this is challenging for at least three reasons. The parameters x might be high dimensional. As I said, they're often the discretization of a field. This distribution is in general non-Gaussian, and we want to capture that non-Gaussian character. And then finally, evaluations of the density themselves, point-wise, might be expensive, because they might, for instance, cost me a run of the forward simulator, which is involved in evaluating the likelihood. But this is kind of a standard setting for Bayesian computation. I have a distribution whose density I can evaluate up to a normalizing constant at any point that I want. And now I want to characterize that distribution. Now, what do you mean by characterizing the distribution? Well, essentially, I want to be able to compute expectations with respect to the distribution. So if I have some function h that I like, I want to be able to compute the expectation of h against pi posterior. And that h could encode, moments. It could be the probability of some event of interest. It could be some marginal that I care about. Any kind of information that I'd like to extract, I can generally write as an integral like this. Okay. So this is kind of the starting point. And under this sort of maybe innocent-seeming starting point, there are a lot of computational challenges, and at least maybe two strategies that are complementary that people need to think about to make this computationally tractable. So on the one hand, as if evaluations of this posterior density are expensive, it's useful to consider approximations of the posterior density, approximations of the forward model that's hiding inside of the posterior density. And a lot of uncertainty quantification is concerned with how to do this. Polynomial approximations, interpolants, emulators, reduced order models, multi-fidelity approaches, maybe neural networks, a whole host of things that one could use to approximate this density. And I'm going to mention those sort of as, again, an important area that I'm not going to discuss in this talk. What I'm going to focus on today are sort of a complementary thing. I think one really needs both. I'm going to focus on how you actually, for instance, draw samples from this posterior, or draw samples from something that lets you characterize expectations of this sort. So efficient and ideally structure exploiting sampling schemes. Okay? Now, In the title of the talk I mentioned I also want to think about sequential problems. The problem that I just showed you here may not be sequential in the sense that maybe I collect all the data and I'm trying to learn parameters, and if I'm trying to learn a permeability, that permeability probably does not evolve in time. But for contrast, let me introduce a more sequential problem. This is a picture borrowed from NCAR. This is kind of a picture of a weather forecasting exercise. So prototypical problem here is something like is numerical weather prediction, where now essentially what I want to do is Bayesian inference in a repeated fashion. And what I might want to do are estimate the state of a dynamical system in a Bayesian way. So I want to characterize the posterior distribution of that state. Given data that I've obtained up until the current time. Maybe I want to characterize the state in the past given data that I've obtained up until today, so that's a smoothing problem as opposed to a filtering problem. And maybe I also have static parameters, so maybe parameters that are evolving, not evolving in time on the same time scale as, say, the data are coming in, so it's essentially static for the purpose of this exercise. Maybe I want to estimate those along with the state. Maybe I want to do joint state and parameter estimation. Okay? And in this context, what we'd really like are recursive kind of online algorithms for characterizing the posterior distribution. Okay. I'm going to dig into this case in more detail, so the first thing I want to do is kind of abstract it. Let's consider just the problem of estimating the state. I'm going to abstract that problem using this graphical model here, where these nodes represent random variables z0 through zn that represent the state of the system at successive times. So you can think about this picture if I discretize time. Each vertical slice here is a different time layer. And this represents the evolution of the state. I have the transition density, which sort of encodes the Markovian dynamics, that is the distribution of the state at time k, conditioned on the distribution of the value of the state at k minus 1. And then I might have observations of some or all of the state, and that's represented by these red nodes here. And that corresponds to this likelihood function here, which is essentially the density of the observations given the state at the particular time. And now what I might want to do, from a Bayesian perspective, is characterize a smoothing solution. So in that sense, using, say, MATLAB notation, I want to look at the joint distribution of all the states from time 0 up until time little k, conditioned on all the data that I've received from time 0 up until time k. And then when new data comes along at time k plus 1, I would like to characterize that new, even larger, even higher dimensional distribution that characterizes the joint distribution of all the states, condition all the data I've obtained anew. Okay? So going from here to here and doing that in a recursive fashion is a smoothing problem. This is a challenging problem for a host of reasons. For one, you can see already we're looking at a distribution whose dimension grows in time. A slightly easier problem that's still of a lot of practical interest is to say, well, let me just look at the most recent marginal of that joint distribution. So rather than looking at the joint distribution of all the z's conditioned on all the y's, let me just look at the distribution of zk conditioned on y0 through k. And then when I get a new piece of data, yk plus 1, let me look at the distribution of zk plus 1 conditioned on y0 through k plus 1. Okay? That's the filtering problem. So we're going to talk about that. Now, a slightly more complicated problem says now, suppose, let me augment this graph with an additional parameter theta. And theta is going to parameterize something about the dynamics that I would like to learn. So now I have my transition density that represents the time discrete dynamics that says, okay, what's the distribution of the state at time k conditioned on the value of the state at time k minus 1 and some parameters that maybe are entering that dynamical model. That's these parameters theta that are highlighted here in blue. And now the fully Bayesian thing to do would be to say, let me look at the joint distribution of all the states and the parameters theta, conditioned on all the data I've obtained up until time k. New data comes along, now everything gets augmented k plus 1, and except I'm conditioning theta on more data. Okay? So that's smoothing and sequential parameter inference, and maybe I really only care about theta, in which case I would like to marginalize out the z's. Okay? So this is kind of the starting point. These are the problems that I'd like to focus on. And what I'd like to do in this talk, is relate these goals to notions of coupling between probability distributions and transport. Okay? So that's really going to be kind of the big picture. I'm going to take these problems and connect them to this notion of transport. Okay? So what do we mean by transport? So let's suppose that I have two probability measures. I'm going to assume they're absolutely continuous, so I'm just going to sort of work with their densities. I have a complicated distribution that whose density I'm going to call pi. And I'm going to use here a banana sort of boomerang distribution as my cartoon for complicated. And I have a simple or tractable distribution with density eta. And for our purposes, let's let it be a standard Gaussian. Okay? Now, this is simple and tractable in the sense that I know how to generate samples from a standard Gaussian easily, IID samples, unweighted. I can generate quadrature rules with respect to a Gaussian. I can do all kinds of things with a Gaussian. The Gaussian is sort of well in hand and a distribution that I can handle. Pi is some more complicated thing. Pi, for instance, might be the posterior distribution in one of these problems that I just described, whose density I can evaluate up to a normalizing constant, but it's not Gaussian, it's perhaps not in some standard family, and I'd like to characterize it in some way. Now, one way of characterizing pi would be to construct a mapping. This is a function t, here from R2 to R2, because these are densities in R2, that takes samples from eta and essentially warps them or transforms them so that they look like samples from pi. Okay? More formally, what that's saying is that if I look at any set under pi, and I look at the pre-image of that set under t, I'm going to get some set over here. And if I measure the probability of that set according to eta, then that corresponds to the probability of that set according to pi. Okay? So formally, the map t pushes forward the reference eta to the target pi. Okay? And if these are densities on Rn, then this map t is a function from Rn to Rn. Okay? Equivalently, I actually might be happy finding the inverse of this map. I might be happy looking for an S that's the inverse of t. I'm going to ask that t be invertible, and S is going to push forward pi to eta. So the notation here with the sub sharp means push forward. So t pushes forward eta to pi, S pushes forward pi to eta. Okay? Now, if I could do either of these things, I would be pretty happy, because if I simply draw samples from my standard Gaussian, evaluate the map t on these samples, I would have samples from pi. And I could evaluate expectations over pi, essentially by doing a change of variables using the mapping t. And I also might be happy enough satisfying these conditions only approximately. And I'll talk about, what do I mean by approximately and how happy is happy enough. That's maybe a judgment question. But I might be content at satisfying these conditions only approximately. Okay? But in general, if I could find a transport map t that deterministically couples my tractable distribution to my intractable distribution, then I have a way of basically characterizing the intractable distribution. Okay? So how to do that? Now, one question you might first ask is, do maps like this exist? And under the conditions that I've sort of implicitly used here, that these are absolutely continuous measures, there's sort of no atoms in these measures, the maps always exist. But now the question is, which map do you want? And there's an infinity of maps that you could consider. So a widely studied choice that you've probably come across before is the notion of an optimal transport map. An optimal transport map. And that is a map that solves the following problem. So among all the maps that say push forward eta to pi, so eta and pi are given distributions, I want to find the map that minimizes some kind of transport cost little c. And what that transport cost might be, for instance, is the distance between x and t of x, or the squared distance between x and t of x. These are different transport costs that have been considered, and solutions of this problem have been characterized in many ways. This problem actually goes all the way back to Monge in the late 1700s, when he was concerned with kind of the military logistical problem of how do I take material over here that's distributed in some way, and how do I transform it to material, think of another sand pile that has a different shape distributed over here. Or I want to move tanks from here to here, or people from here to here. How do I do that efficiently in a way that minimizes some sort of overall transport cost? Okay. So optimal maps are very nice. They've been studied, sort of a resurgence of interest in optimal transport in mathematics, many nice properties. But in general, solving this problem, this Monge problem, is pretty challenging in general continuous cases. Okay? There's been a lot of work recently on discrete optimal transport. There are fast methods for that. But I think the continuous problem is still beyond kind of 2 or 3 dimensions, pretty challenging. So the map that we're going to use, that's going to be kind of the building block for a lot of the couplings I'm going to describe later on, is a different kind of map. It's a triangular map called the Noth-Rosenblatt rearrangement. Or if you're a statistician, you can think of this as Rosenblatt transformation. If you're a computational geometer, maybe you're more familiar with Knuth. But the idea is as follows. So we have a map. Again, it's a function from Rn to Rn. But now the first component of that function is restricted to depend only on the first input, the second on the first 2 inputs, so on and so forth. Now this map also exists under the same conditions, lack of atoms. It's unique once you specify the ordering. But it has a lot of nice numerical features. For one, the Jacobian of this map is a lower triangular matrix, so the Jacobian determinant is easy to evaluate, and we're going to have to do that a lot. The inverse map is also lower triangular. And maybe a more fundamental reason that this triangular map is going to be useful is that it exposes marginals of the target in a useful way. So what do I mean by that? I mean that the marginal distribution of the first 2 components of pi, which correspond to the first 2 rows of this map, are written here as a function of only 2 variables. Whereas if I had a general non-triangular map, those marginals would have to be written as functions of, say, all n variables in general. Okay? So being able to expose marginals as function of a small number of variables is going to be helpful for us as we go on. Also, you can numerically approximate or parameterize maps in this family pretty nicely using ideas from monotone regression. So this is an idea from monotone regression where basically I say, I would like to guarantee monotonicity of this map in a certain sense. And that sense is that the kth component, t super k, has a positive derivative with respect to xk for any input. Okay? How can I guarantee that? Well, one way is to simply take whatever my favorite basis is, a and b, and embed it in the skeleton of the monotone parameterization that guarantees that this thing is going to be monotone increasing with respect to its last argument, with respect to xk. And here I use exponential. It's a positive function. One could imagine using a square or like squared plus some epsilon if I want to maintain some strict monotonicity. Various things that you can embed in this monotone parameterization, and then ak and bk can be, in some sense, up to you. Polynomials, radial basis functions, various other things, but this skeleton ensures monotonicity with respect to xk. So we're going to use numerical approximations or numerical parameterizations of Rosenblatt maps as a building block for more complicated couplings. Okay. So how do we find such a map? So what's the core computational problem? The core problem is essentially something like variational Bayesian inference. So if you do variational Bayes, this should be familiar. And the idea is, over some space of monotone lower triangular maps, T triangle, I want to minimize the KL divergence between the push forward of my reference under T and the target pi. Okay? And I can rewrite that as follows. I want to minimize the KL divergence between the reference here on the left and the pullback of the target under T. Okay? And if that is 0, then those two distributions are equal and I'm done. And insofar as that's not 0, then I have some bias and we can characterize that. But this problem is actually tractable. Why? Because especially if you think about the KL divergence here written on the right, this involves an expectation over the reference, which is tractable. So I can approximate that expectation using Monte Carlo or quadrature or whatever I might like. I might want to compute, then I can essentially convert this to like a sample average. I can just do a sample average approximation. I could also do stochastic approximation if I wanted. And then I can use evaluations of pi and its gradients and solve this problem for a given parameterization of the map. Okay? And this is going to be something that is not MC-MC and it's not importance sampling. It's going to do something qualitatively different than either of those approaches. So let me give you a very simple example where again I have my banana, my target distribution pi. My reference is this standard Gaussian right here. And I put them on the same axes on purpose because the target is very much in the tails of the reference here. This is about this is exactly 6 standard deviations away from the mean of the reference. And I'm going to solve that optimization problem. I took away some constant terms, and this effectively becomes the optimization objective. And you can kind of see what this optimization objective is doing. So it's going to look for maps T that take samples from eta and then move those samples into regions where log pi is large, so that minus log pi is small, in order to minimize this overall objective. So what that's saying is saying, take the samples, find a T that pushes samples from eta to regions of high pi, of high density. At the same time, don't throw all the samples together to the same point. This is essentially, you could think of this as kind of a repulsion penalty. Okay? But this just, it's not like we impose these terms. This follows naturally from KL divergence. I'm just interpreting the terms that come from KL divergence. We're going to parameterize the map. I think for those little functions a and b, I'm going to use polynomials of degree 2. We're going to optimize over the coefficients of those functions. I'm going to approximate this here with Monte Carlo, and then just solve the problem. Okay, and in particular, I'm going to use BFGS to solve the problem. I'm going to fix a certain number of samples, and I'm going to use BFGS. And the orange dots that I'm going to show you here in this little animation are basically samples that are pushed forward through the current guess of the map. And my initial guess for the map is going to be an identity. So the samples are going to be sitting right on the reference. And then one iteration of BFGS, 2, 3, we've found basically tweaked the map coefficient so that now the samples are sitting right on the target. Okay. So and you could sort of iterate on it, but the particles are not going to do much more. So from one perspective, you could also think about this sort of optimization problem as inducing a flow of these particles, but we're not parameterizing where the particles go individually. We're parameterizing the overall transformation. We're parameterizing the displacement through the map. So so with this, we'd be happy, and essentially with this map in hand, I can draw samples from the reference and basically get these orange dots here right on the target, and I can evaluate expectations using those. So what are some features of this? We have moved samples rather than just reweighing them, and I think this is really important, say, as a contrast with importance sampling, things like that. With a map in hand, the samples are independent and cheap because I just need to evaluate the map on samples from Ada. Now you might ask, okay, well, given that I've numerically parameterized the map in some space of monotone lower triangular functions, how well have I done? Well, I know if that space is rich enough, it would include the Rosenblatt rearrangement and I would have a KL divergence of 0, but in practice probably does not include the Rosenblatt rearrangement. So we'd like to sort of assess something about how well we've done. Well, the KL divergence is kind of what we're trying to optimize, but you can actually show that the KL divergence is asymptotically equal to this variance criterion. And the variance criterion is something that you can evaluate pretty easily, even with an unnormalized target density in hand. And it has a good interpretation. So here I put a pi bar, I put the bar on pi to emphasize that I don't know the normalization constant of pi. If I pull back pi by my current map, and the map were excellent, then the pullback of pi under the map would look Gaussian. And here I'm looking at the ratio, or the log of the ratio of a Gaussian to whatever that pullback distribution is. Now, if I were done, if t inverse pi were Gaussian with some unknown normalization constant, this ratio would be constant, and its variance would be 0. Okay? So insofar as this log ratio departs from being constant, then the variance departs from being 0, and that corresponds to the KL divergence departing from 0. Okay? So this is a convergence criterion that you can use to check, and asymptotically, it's 1/2 of the KL divergence. So having basically chosen some parameterized space of maps, you now kind of have a fork in the road. You have a choice. You can accept the bias, in other words, estimate this criterion and say, is this large enough, small enough for my purposes, or do I need to make it smaller? If you don't like the level of bias, you can increase the complexity of the map T, so find a richer space of maps to work with. Or you can take that pullback and do something with it. So, for instance, pi was my original distribution. Suppose T is a very restricted, maybe coarse space of maps. Not quite enough to Gaussianize the target. The target is still closer to a Gaussian in the sense of KL divergence than what I started with. And that can then be a target for other sampling schemes. So I'll just mention kind of an aside. Sampling the pullback can be used as an idea of kind of preconditioning complex distributions. And so some work we've done recently, I will just talk about this in this one slide, is to say, learn a map on the fly and perform MC-MC on the pullback. And as you get more and more MC-MC samples, use that to improve your estimate of the map and iterate back and forth. And so that will take, for instance, a target that looks like this. And with a low order map, say of some restricted space, I can't quite Gaussianize the target, but I can make it look a lot closer to Gaussian. And this is far easier to sample with MC-MC than this is. Okay? So this is just one sort of option in this fork in the road. You can work on the pullback, you can adaptively refine the map, or you can sort of precondition your standard sampling scheme. But what I want to emphasize here, I don't want to sort of advocate, doing this or that in particular. I just want to say this is a framework within you have many choices. And also, this triangular parameterization that I showed is just sort of one of many, I'd say, variational constructions for constructing transports between distributions. And another very interesting recent method is Stein variational gradient descent. There's the notion of normalizing flows that's appeared in the machine learning literature, where you're parameterizing the maps using essentially neural networks or compositions of simple functions. People have tried to write time one flows of ODEs that transport particles from a reference to a target, this notion of Gibbs flow. These are necessarily approximate. People have tried to solve, sort of elliptic PDEs to come up with potentials that give you maps. Implicit sampling is another sort of method for constructing transports. Some of these are necessarily approximate in the sense that they don't have like a refinement strategy. Some of them are, as you refine more particles, as you refine the kernel. But all of these methods essentially use this idea of transporting measures, connecting a very simple measure to a more complicated measure, and trying to find a transformation that's going to couple the two. Okay? So all these are very nice, but let's say they all kind of have one underlying challenge, which is how do you do this in high dimensions? So I showed you a cartoon that was two-dimensional. We can parameterize the maps. We can do a super good job. But what if that cartoon were 1,000-dimensional? Essentially, then I would be looking for functions from R1000 to R1000, and that's pretty nasty and seems sort of painful. So the major bottleneck, I would say, is the representation of the map, the cardinality of the map basis, if you're parameterizing the maps explicitly like we are. But this bottleneck even shows up if you're using a non-parametric approach. Okay? Because you still need a lot of information to represent those transformations. So for the remainder of the talk, I want to kind of sort of expound on this theme of how can we make the construction or representation of high-dimensional maps, high-dimensional transports, tractable. Okay? And to that end, I want to consider, well, we need some structure that we can exploit. And I'd like to consider the idea of exploiting the Markov structure of the target distribution. So this is now going to be our connection to graphical models. And structure in the target distribution is going to lead to various low-dimensional properties of transport maps. And we've sort of figured out at least 3 of them. I'm going to focus on the ones in blue. I'm going to focus on the notion of decomposable transport maps. And time permitting, I'll talk about transport maps that are low rank after a transformation. And I'll explain exactly what these are. Okay. So what do I mean by the Markov structure of the target distribution? So suppose I have my target distribution with this density pi that's strictly positive. This is a density in Rn, so this is the joint distribution of n real-valued random variables z1 through zn. I can represent conditional independence relationships among these variables z1 through zn using a graphical model. In particular here I'm going to use an undirected graphical model, so a Markov random field, where the absence of an edge indicates conditional independence. So the fact that, say, these 2 edges here are not connected, or these 2 nodes are not connected by an edge, means that those 2 nodes are independent of each other, conditioned on all the other nodes in the graph. Okay? So the sparser the graph, the more conditional independence relationships are encoded. Okay? And very often, this graphical structure is something that we impose or that we know or that's part of our model. There's a whole other business, which is how do I learn the graphical structure if I simply have data and I don't know it, but that's another business. It's a very interesting business, but I won't talk about that today. So I'll assume that we have this graphical model in hand. And the question is, okay, if I have this graphical model in hand for pi, what can I say about the transports? And what in particular can I say about the structure of the transports before I actually compute them? And so what can I say about them in particular in a sense that's going to be useful for computing them, make their computation more tractable in high dimensions? So I'll paraphrase a theorem from a recent work, which is basically that decomposable graphical models for pi, for the target, lead to decomposable maps T, provided that the reference is a product of its marginals. So if the reference for the purposes of this talk is a standard Gaussian, then this is automatically satisfied. And it basically says that if my graphical model for pi admits a certain decomposition, then that decomposition leads to a factorization of the maps. And what do I mean by decomposable map? A decomposable map is, say, this T, which is generically a function from Rn to Rn, here R6 to R6, that's going to factorize as the composition of a finite number of maps of low effective dimension. And by low effective dimension, I mean that these maps differ from the identity only in small groups of variables at a time. So this map here is effectively of dimension 3, this one here is effectively of dimension 4, and this is effectively dimension 3. And all of these, as you know, are triangular Upter permutations. So they're kind of using that Rosenblatt structure, but we're going to kind of start permuting it around and doing funny things with it. Okay. So what do I mean by that? So let's just consider a graph here. So this theorem, I'm kind of paraphrasing a much more complicated theorem, but applies to general graphs. And here I have this particular graph here. It happens to be chordal, but that's not too important. This is a 6-node graph, and I'm going to consider, there's many decompositions I could consider. Let's consider the following decomposition, where S is a separator between A and B. So basically, to go from a node in A to the node in B, I have to walk through S. And this particular decomposition is going to give us a certain factorization of the map, as follows. So let's consider a map that is the identity on 3 nodes. So it's the identity on all of the nodes that are associated with the set B. And it departs from the identity on the nodes that are associated with A and S. And in particular, it's going to have this kind of upper triangular structure where I expose the marginals of the nodes in the separator set S. Okay? So this is upper triangular, so this is essentially 3-dimensional, and this is a 2-dimensional block. Okay? And then this is the identity. Now, suppose I construct this map such that it pushes forward a reference of 3 dimensions to the marginal distribution of the nodes in A and S. Okay? Now, I don't actually want to construct this map because in general I don't know the marginal distribution of the nodes in A and S, but I'm just going to say hypothetically, suppose I did construct such a map. Okay. If I then pulled back the target density by that map, so the super sharp here means applying T1 inverse to pi. If I pulled back that target density, I'm going to end up with a new target distribution that has a different Markov structure. And that Markov structure is basically one that erases all the edges connecting nodes in S to nodes in A. So I've sparsified the graph, okay, by constructing this hypothetical map, T1. Okay. Now, the maps, I can continue constructing them in sequence. So the single map that only was 3-dimensional didn't really do the job, but now I can consider a new decomposition of what's left over. And this is now, I have A here and S here, so now I have a 4-dimensional map that's going to sparsify the graph when I pull back by it. And when I'm done, now I have a click, so there's really nothing more I can do. So I have a 3-dimensional map that's going to handle it. Now, this kind of cartoon, the upshot of it is that what we've shown is the existence of a map that factorizes, that decomposes, based on the existence of these two graph decompositions that we applied in sequence. So because I was able to decompose this graph with in these two stages, we're actually able to say that there exists a map from R6 to R6 that factorizes as follows, with basically this 3-dimensional, 4-dimensional, 3-dimensional component that will push forward any reference, standard Gaussian reference, to any target that has this particular Markov structure. Okay? And I can predict this simply using these graph operations without actually computing the map yet. So now, having done this, so having known the graph for the target distribution, I can say, well, now I want to compute the map, and rather than just parameterizing functions from R6 to R6, let me parameterize functions that are at most 4-dimensional. Here the savings maybe seem modest, but let me look for maps in this form. So this is my ansatz for the kinds of maps that I want to look for. Okay? And I could do this now all at once. I parameterize all these guys and look for all the coefficients. I can do that all at once. Okay? So generically, this is something that one can apply. If they're graph decompositions, you can factorize the maps. What I'd like to do now is go one step further, which is to say, what if I actually don't want to find these all at once? What if I actually want to find the maps and the compositions sequentially, one at a time? Because that's an even smaller optimization problem that could be much more tractable. That would be much nicer. It turns out that for that, we need some sort of integrability conditions, but in certain problems, those are pretty easily satisfied. And the particular problem that I want to now come back to is state space models. Okay? So state space models, the graph for the posterior, so if I condition the z's on all the y's, then that doesn't really change the structure here. The graph for the posterior is a chain graph. Okay? So this is about as simple as you can get. Now, what is a decomposition of this chain graph? Well, I can consider this node to be A, this to be my separator node, and the rest to be B. I'm ignoring the red. I've conditioned on the red and I still basically just have the blue node. So A, S, B. So now essentially what I want to do is look for an upper triangular map that is of dimension twice the state, twice whatever the dimension of Z is, and embed that in an identity map and find that map, and now pull back by it, and now I'm going to find the next map. So now this is A, that's S, this is B. I'm going to find another 2-dimensional map, and I'm going to sort of continue iterating like that. Now, the thing that links the two is that the target for this map is the joint distribution of Z1 and Z2 conditioned on Y0 through Y2, but pulled back through the first map. So there's a little bit of the first map, B0, sitting here in the target distribution. So in the first map, I basically exposed the filtering marginal I exposed the marginal of Z1 conditioned in Y0 through Y1, and I'm expressing that marginal using this map B0. In filtering, the previous filtering distribution is essentially the prior for the next inference step. So that prior sits here inside the target. We essentially kind of reparameterize the distribution, and now I find this 2-dimensional map, and I continue so on and so forth. Okay? So if I do this sort of sequence of things, essentially what I'm doing at each stage, when I solve a problem like this, if you're a filtering person, you would recognize this as lag 1 smoothing. I'm doing smoothing back one step in time. My target is essentially the joint distribution of Z3 and Z2 conditioned on Y0 through Y3 up to some parameterizations, up to some nonlinear transformations. But I do a sequence of lag 1 smoothing problems, and I can now basically put together all of those maps that I found and solve the entire smoothing problem, the whole n-step smoothing problem. Okay? So what have I done? If I do basically walk through all these things, all these little maps B solve the filtering problem. These maps curly M, which are these guys here, solve the lag 1 smoothing problem. And if I compose all these maps T together, I have the full Bayesian solution. I solve the entire Bayesian problem. Maybe if I kind of write out these maps more explicitly, this kind of shows you what's happening. So here's the first map, here's the second map. Now suppose I have a new piece of data and corresponding new state. Then I append this next map to the composition. And these are fixed. T0 and T1 are fixed. I append T2. There's no need to recompute the previous maps. Okay? So what I've done now is I'm essentially taken, this map here that's in general dense and high dimensional, and I've decomposed it into a sequence of simpler maps that I can find one at a time. Okay? You might ask, okay, how is smoothing actually happening? So if I observe data corresponding to this map, suppose I've observed, say, 3 pieces of data and now I observe a 4th, that ought to, in principle, affect the marginal distribution of the very first state. So maybe going back to this picture here, if I observe data here, yn, that actually ought to affect my knowledge of the state, in principle, going all the way back to 0. Of course, correlations will decay, and eventually that'll be a very small update. But how does that happen when I compose maps? Well, essentially, I have a distribution here that's the standard Gaussian. I operate on that standard Gaussian, and I get, say, some output here, A2. That is going to give me an input to this map here. Which one's going to, so this is going to give me an input here, and then x2, and that's going to give me an input here. So by basically putting a new transformation here, I'm warping what comes out of the other side of the composition of maps. So that's how smoothing is happening. You can actually think about this as message passing. You can think about this as basically when you compose the maps, you're passing information backwards in time. So, so maybe just some intuition for the smoothing. Each lag1 smoothing map implements the following factorization. So I have the joint distribution of zk, zk minus 1, condition all the data. I factor it as follows, where I have the most recent filtering marginal, and then the particular upper triangular structure of the map says give me the distribution of zk minus 1 conditioned on zk, which simplifies as follows. And then the composition of maps basically implements this backward recursion. So the previous state conditioned on the most recent state, the previous state considered on the next most recent state, so on and so forth. Okay. So this factorization here, if you squint at it, is tightly related to the upper triangular structure of the maps that we compute. Okay. Maybe that takes a bit of squinting. But so let me just kind of step back and say, what do we have? You could think about this as really kind of now a meta-algorithm, a variational algorithm for smoothing, a variational Bayesian algorithm for smoothing, where the core computational step is to do lag1 smoothing and compute these maps, curly M0, curly M1. We embed them into the identity map. We evaluate them for the pole Bayesian solution. We walk through the state space model in a single pass. And if you want to then evaluate the smoothing marginal at some point, you just come back and you compose the maps. In the linear Gaussian world, this might be a little bit familiar. This is actually kind of a non-linear, non-Gaussian generalization of the RTS smoother. So the RTS smoother, kind of classical algorithm from I think the 70s or late 60s, where you basically do a whole bunch of smoothing, it's kind of smoothing version of the Kalman filter. You basically do a bunch of lag1 smoothings, you store some things, a bunch of matrices and vectors, and when you want to evaluate a particular smoothing marginal, you go back and you reassemble those matrices and vectors in a particular way. Now we're storing maps, and we're re-evaluating them in a particular way. Okay. Now, from the algorithmic perspective, of course, this is biased insofar as we numerically approximate each of these maps. And as I said before, you can accept the bias, or you can reduce it. You can compute weights. You can do importance sampling to correct for it, sort of all these different things you might want to do. You can generalize this idea now to joint state and parameter estimation. So I have this parameter theta sitting up here. And now I want to kind of characterize the joint distribution of theta and z conditioned on all these y's. And what do the graph decompositions look like? So here's just a particular example where I have a two-dimensional theta. I have the parameter mu and parameter phi, and here's my state. This is the sequence of graph decompositions we're going to do. So now the static parameters are always part of the separator set. And then I sparsify, and I have a new decomposition. The static parameters are again part of the separator set. And I sparsify, so on and so forth. Okay. So in doing that, I'm still building this composition recursively. So now this lets me do fully Bayesian joint state and parameter estimation. And the maps that I build are going to look like this. This is just a generalization of what we had before, but now there's this blue part at the head of every single map that corresponds to the static parameters. And these maps are, again, triangular up to a permutation, and they depart from the identity only on a subset of the variables. Okay? So put all this stuff together, and we're doing parameter inference. So let me just give you an example. This is kind of a simple example. I have this dynamical model. It's a stochastic volatility model. This represents like the log volatility of some asset. In the example I'm going to give you, we use real data for the dollar-pound exchange rate. And and the parameters mu and phi are unknown, and what I observe is kind of non-linearly related to the state here. So this is basically the volatility. If you think of this, the exponential, this is a variance, essentially. Exponential of z is a variance. The Markov structure for the target distribution is exactly what we just looked at. So I'll notice this is not a chain. This has cycles. I mean, this is sort of not entirely trivial structure. How does it all work? So we're going to infer the volatility of the pound-dollar exchange rate starting in 1981. Here we're just going to go for 500 days, so this is time in days. Filtering marginals are in blue. So the median is the solid line, and I think 25% and 75% quantiles, or maybe 10 and 90% are the dashed lines. The smoothing marginals are in red. And you can see, okay, they ought to agree on the very last time, because the filtering and smoothing coincide when you've conditioned all the data. But as you go back, they depart from each other, and indeed the smoothing is a bit narrower in general than the filtering. So the information here does propagate backwards fairly far. Let me compare this to what I would do if I did MCMC. So with MCMC, this is not a sequential algorithm. I have to basically take all the data at once, do joint inference on all the state here. So it's going to be, in this, I think we did about 900 days, so a 902-dimensional problem with MCMC, which is actually not entirely trivial. But once we do that, then the smoothing marginals in red, computed with the map, agree very nicely with the MCMC solution in black. And I can actually now look at the same thing for sequential parameter estimation. So the map algorithm is sequentially updating the distribution of the parameters. So this is the parameter mu as a function of time. The solid lines are the map, the dashed lines are MCMC. But each MCMC slice here is an entirely separate calculation, not a sequential algorithm. But we're just doing it for reference. And you can see there's some mismatch. Of course, this is due in part to our numerical approximation of the maps. And in general, the parameter estimation is less forgiving than the smoothing, but nonetheless, we seem to be doing pretty well. For the other parameter, seem to be doing pretty well. And then we can actually take that smoothing and make it very, very long time. So now I'm going to solve a 9,000 dimensional problem, 9,000 days of data. And because 9,000 days actually bring us pretty close to the recent past, in the log, in the volatility of the pound-dollar exchange rate, you can see a couple events. So this here, this blip here, this jump in volatility is the fall 2008 financial crisis. And this blip here, briefer, is Brexit. And this is just from, this is from real data. This is from actual daily volatilities. Okay. But this is a very long smoothing calculation. And again, we're kind of comparing the map and MCMC, and they continue to track each other pretty well. So we've solved effectively here kind of a roughly 9,000 dimensional problem, but by computing maps that are at most 4-dimensional at each stage. 2 static parameters and then 2 times the state dimension. Okay. Now, how well are we doing kind of by our own diagnostics? Well, the variance diagnostics say for this is different versions of the problem. If you just did a Laplace approximation, this variance diagnostic is order 5. If you did the best linear map, so this is sort of best in KL divergence, the variance diagnostic degrees. And if you let your map here, we kind of choose the map order adaptively, depending on a local variance diagnostic. But if we cap the degree at 7, then you can do a whole lot better. Now, I want to emphasize there are some open theoretical questions here. I say smoothing is more forgiving than parameter estimation. Smoothing is forgiving, filtering in general is forgiving because particle filters require, even if you say, let's go to SMC method, it's the same issue. Particle filters require in some sense that you forget about the prior, or the dynamics of the system are dissipative so that if you make an error in the prior, over time you're going to forget about that error. Otherwise, in general, particle filters would not work. Parameter estimation does not have that nice feature. Those parameters theta are never forgotten about. They're always there. The only thing that maybe helps you is that over time the posterior ought to concentrate and become more Gaussian, kind of Bernstein-von Mises-like, but that happens super slowly. That happens roughly, at the rate of the square root, 1 over the square root of the number of data points. So that's a much, much slower process. So it's actually kind of in general open how the error in the approximation of the parameter posterior evolves over time for maps of fixed order. I think that in general it's going to grow, but that's something that I think is yet to be characterized. Okay. So any questions on this before I talk about this last little bit? Yes?
Yeah, how about the flexibility of this transport map when you have, for example, transform a unimodal distribution in, for example, a multimodal distribution, or when you have like an infinite support to a finite support distribution?
Yeah. So in general, in principle, the maps exist. There is always a map that'll take a unimodal to a bimodal. But now it comes down to the parameterization. So now this comes down to the kind of the numerical issue that I didn't talk about as much. But here, for instance, parameterizing the map with polynomials or polynomials embedded in that monotone parameterization may not be so efficient, but doing something like radial basis functions actually works much better. So if you imagine, suppose I have like a uniform, say Gaussian on this, suppose I have a one-dimensional map, and I have a reference that's, say, Gaussian on the horizontal axis, and I have a target that's bimodal like that. Then the map that's going to do the job is essentially has to have kind of two plateaus. The map has to kind of do that, something like that. So this is a monotone map that roughly transforms. So I need to be able to represent functions like this. And so multimodality corresponds to kind of local features in the map. So for those kinds of problems, of course, they're more challenging because now radial basis functions, where do you put their centers, blah, blah. But in general, like, you can do it using radial basis functions. The other thing that I would say is that, non-parametric representations of the map, a la Stein variational gradient descent, as we've been discussing with Nicholas, also can do a nice job with problems like that. So that might be a good situation in which maybe to leave fully parametric representations or introduce some non-parametric part to representation of the map. Okay. So infinite to finite support, typically what we do there is just transform the finite support to something that has infinite support. So you could think of that as composing the maps. So we're looking for a map from R to R, but then we take R and we have another map that maps R to like 0, 1 or whatever it might be. But again, you could think of that as just part of the numerical trickery of approximating the map. Yeah, good question.
So when you work these state space models with particle filtering methods, you always have the degeneracy problem regardless of what you do. So do you have to reinitialize at any time to address? Does this come at all?
Here, actually not. That's the beautiful thing that we're pretty happy with. And I think it's because we're solving an optimization problem at every step. So at every step when we find this 2-dimensional or 4-dimensional map, we are moving the particles to where they need to be. The particles are only there as a device to kind of represent the expectation. But at every single step, we're doing kind of what I showed in that cartoon of taking the particles and moving them where they need to be. So the error here really, so in these examples, we didn't have to reinitialize anything. Where the error shows up, insofar as it shows up, is again in this B. So basically, if I have a bad representation of the previous filtering distribution, that could make my representation of the target look bad. But that's where, okay, you need to forget the prior a little bit. And if the dynamics are a bit dissipative, then this thing is going to forget this argument a little bit here. But there's no and the particles are just sort of local at each time. So there's no particle degeneracy that comes from like accumulating weights and keeping track of the trajectories and all that kind of stuff. So, yeah. Okay. So the last thing I want to talk about is kind of maybe when conditional independence fails. Or when conditional independence is not enough to solve the problem. So I talked about decomposability of the maps. That depends on graph decompositions. And the nice thing about all the examples that I showed you is that the dimensions of the maps that I found at every single step was decoupled from the full dimension of the problem. So I'd say, oh, it's a 9,000 dimensional problem, which sounds very impressive, but in practice I was just finding 2 or 4 dimensional maps at every single step. So I didn't care how long you make the time series, only 2 or 4 dimensional maps. But there are problems for which that is not true. For instance, grid graphs. Grid graphs are awfully annoying because now, if I refine my discretization, suppose I have a grid graph that represents a spatial field, now the size of that separator set is going to increase, the size of all the maps is going to increase, so on and so forth. But in some problems, there is kind of an alternative source of low dimensionality, which I'm going to kind of loosely call low rank structure. And I'm just giving you, maybe it's best illustrated by an example. So suppose I have pi as the posterior density of some Bayesian inference problem. So here's the posterior, here's my likelihood, y given z, and here's my prior. Let me say, okay, I don't need to find all the maps all at once. That's maybe part of the philosophy of this. I can find one map, I can pull back by it, I can find the next map, I can sort of solve the problem in stages. So let me begin with a map that I know well, the map that pushes forward the reference to the prior. Okay? If the prior is Gaussian, then this is a linear map. If the prior is something typically that I made up, then I ought to be able to write down this map. Let's take that map and let's pull back the target, pull back the posterior by the prior map. So that's going to give me this pi hat post. This is the pullback of the original posterior under the prior map. And I can write down its density. Its density basically looks like the likelihood function composed with the prior map times a standard Gaussian reference. So essentially what that's done is to sort of taken the prior, Gaussianized it, and then pushed the complexity into the likelihood function itself. Okay? So, like I say, have I made any progress at all? Well, the question is now, is this distribution somehow easier to deal with than the original distribution? And one sense in which that distribution might be easier to deal with is to consider the following ratio and the kind of sort of score function. So let me look at the ratio of this target, pi hat post, this is the new target, to the standard Gaussian reference. Okay? Let me call that R. And now let me look at the expectation of the outer product of gradients of log R. Okay? This is a matrix. This is an n by n matrix. And here I'm taking expectation with respect to eta. You could actually do certain other measures. If this thing is of rank k, suppose it's of exactly rank k, just to make it easy, then that actually says that there exists a rotation that I could apply to this target pi hat post such that the resulting rotated distribution departs from the reference only in k variables. So I can find some q, which actually comes from the eigenvectors of this matrix, such that basically this thing looks like the reference in dimensions k plus 1 through n, and then something arbitrarily different from the reference in dimensions 1 through k. So that says this target, after transformation by the prior map, departs from the reference only in a subspace, only in the low-dimensional subspace. Okay? So maybe conceptually what's happened is I've taken a grid graph, if that's the representation for my prior, and then I apply the prior map and I apply some rotation q, and now I have a bunch of disconnected nodes, so I'm essentially done here, and then I have a connected component. Okay? But this connected component is hopefully lower dimensional, and that's something I can deal with. And the corollary to that is then, well, I can actually now write a transport that pushes forward a reference to this distribution with this particular IMAP that is basically the identity on variables k plus 1 through n, and then something strange on variables 1 through k. Okay? And then if I unroll the whole thing, the composition of the prior map, composed with the rotation, composed with this new map, pushes forward the reference to the posterior. Okay. Now, why would this ever happen? This actually happens in inverse problems quite a lot because the data may only inform a small subset of the directions in the parameter space. So I might have a lot of uninformed directions. I might have identifiability issues that are essentially constrained by the prior. The data are only going to basically allow the update from the prior to the posterior to be confined to a low dimensional space. Here, this is linear dimension reduction. We're looking for a linear space in which that update lives. Okay. So let me just give you an example here. This is a spatial statistical problem. This is the log Gaussian Cox process where I have some latent field z. Latent field z, its exponential is like z is like the intensity of a Poisson process, and then I observe counts from the Poisson process y. So this could be like, I don't know, you're doing forestry and you're looking for like the counts of trees in a given cell and how many of those trees do I see in any given sort of kilometer by kilometer cell. And I want to infer this latent field, and I assume it has some smoothness that's imposed through the prior. In principle, this is a high-dimensional problem, say a 64 by 64 grid, so a 4,000-dimensional problem. I happen to observe it rather sparsely with only 30 observations, and then we can write the posterior density here. The IMAP for the prior is a grid. Seems unfortunate. But if I do this thing and I compute this matrix here, this matrix is actually exactly rank 30. Not even like numerical rank 30. It's exactly rank 30. And that's no coincidence because I only observed it in 30 places. And the observations here are local. This generalizes, so if the observations were non-local, then maybe this thing wouldn't be exactly 30. If some of the observations are redundant, then maybe the rank, then we can start to worry about numerical rank and approximation. But in this simple example, the rank is precisely 30. And I can essentially deflate the problem and compute a 30-dimensional map, and now solve the problem. So here's the truth, here's a posterior sample, here's the posterior mean, and I compare that to MCMC. So the top row is the map, here's the mean and the variance field. Same thing with MCMC, and within the eyeball norm, they match quite well. Okay. So this is a different kind of structure. This sort of anecdote or example motivates a larger question, which is, okay, what if the low-dimensional structure is not exact? So what if now we're worrying about approximation? So let me kind of abstract the problem as follows. So rather than my posterior here, suppose I want to construct some approximate posterior pi post tilde, where the approximation consists of two things. replacing the likelihood with some positive function L tilde, and taking the parameters x and projecting them onto an R-dimensional subspace with some rank R projector PR. Okay. Among all rank R projectors PR and all positive functions L tilde, what is the best approximation in that class? So this is saying, okay, I want to, by sort of my ansatz is I want to approximate my posterior with the distribution that it updates the prior only in R dimensions. What is such a best approximation? In the linear Gaussian case, I can solve this problem exactly. I can characterize an optimal approximation. In the non-Gaussian case, it's unclear that a best approximation always exists, but with some ongoing work, we're trying to construct sort of certified or controlled approximations that give you upper bounds on the KL divergence. And then, given that kind of approximation class, this is a problem that I can approximate using maps, or that I can tackle using maps of dimensions only up to R. Okay. So that's ongoing work, and that hopefully will come out in the next couple weeks. So I'll just wrap up. The overall sort of maybe take-home message is that you can solve Bayesian inference problems by constructing transports through coupling complicated distributions to simple measures.